Good afternoon, everyone. This is Duffy, and I am here with episode number 31 of the Echo Live Office Hours. I hope you all are out there and doing okay. Let me know in the comments if you're checking in with us, but it'll be really good to see everybody here today. Today is kind of an interesting episode. I'm actually going to be kind of talking through what I've been doing to do some testing with OpenShift. And so if you've ever wanted to kind of explore OpenShift and how you might be able to set up an environment in which to do that, leveraging some open source technology, this might be kind of a kind of an interesting way to jump in. And I'm going to share a lot about that. Hey, Khalid, good to see you. Thank you for joining. We published number 31 here. I just realized that it's not published. Okay, so as always, you can actually always go to our HackMD, which is published now, so you should be able to see it, but I'll put a link up in the chat. I want to make sure everybody can hear me okay. Give me a thumbs up if everything's working out all right. And I will begin sharing the HackMD, and we'll start going through notes. So, oh, nice. They got a little inset thing now. That's cool. New things in StreamYard. All right. So this is our notes for today, and you can find them just by going to the link here on the lower right, hackmd/@echo-live, and you'll be able to see the most recent published one. That's where the notes are. Lots of really great stuff happening this week. We've announced the Cilium Service Mesh beta program. I'm pretty sure that Liz announced this in the UK time slot last week. But if you haven't checked it out, definitely do so. If you're curious about how eBPF Cilium Service Mesh might help, this is a beta program, and we're looking for people to come and join us and experience the beta. So if you've been considering Service Mesh and want to see like some of the other options that are out there, this is a really good place to jump in. Another article from News of the Week is how we used eBPF to build a programmable packet filtering in a Magic Firewall. So this is a great Cloudflare blog that talks about leveraging BPF to do blocks for Cloudflare events. I mean, you can imagine their problem is pretty specific and it's like a hard problem to solve, wherein they want to be able to mitigate things like DOS attacks or distributed denial of service attacks, right? Where you have hundreds or maybe thousands of sources that are all attacking a particular endpoint, and you want to be able to lock that down. And what's interesting about that is traditionally in networking, you always want to try and figure out a way to shut that traffic down as close to the source as you can get, because that's going to be the most effective way. So ideally, you'd be able to find wherever the source of traffic is and shut it down. In the case of a distributed denial of service, that's much harder, right? Because it could be coming from way more than one source. It could be coming in through peers, different BGP peers. It could be, the IP addresses that they're using to do the attack could be changing or mutating over time. And so it becomes a pretty hard problem to solve. And so this is some of the tooling that Cloudflare uses to actually build this stuff. So pretty cool stuff. Yeah, leveraging the match. And then basically being able to shut down that traffic when they determine that traffic should be shut down. So really great article. If you're interested in it, definitely check it out. Not going to spend too much time on it today, but it looks like a really fun one to dig into. I've also had a blog on NewStack talking about how eBPF streamlines the service mesh. And so this is an article written by Thomas Graf. And it really gets into some really great stuff about like the problem and how it's solved and what we do to actually improve things. I think in a future episode, we might really do kind of like a lunch and learn sort of episode around this, because I'm definitely seeing a lot of interest in this particular problem and in this article in specific. But what it highlights is that a couple of different key pieces, which for me really resonated, and I think might resonate for a lot of folks, which are like, kind of thinking through the problem of what a service mesh is, how it works, what we're doing with it, and like what are some things that we can do to kind of accelerate or to be able to deliver on some of the promises of service mesh, but with eBPF. And so this article really digs into kind of like the use cases, enters into some of the detail and how it all works. There is a piece to this that I think is very interesting. So there's this blog, and then I think we also have blogs on Cilium. Here we go. Nope, that's the same blog. There was a diagram in here that I wanted to spend a little moment with. Here we go. This is one of my favorite diagrams in this article, and I really want to kind of spend a minute with it because I found it to be very educational for me, especially. I mean, like when working through like what Cilium means to people and how it works and all of that other stuff. And it really came up in a really kind of an interesting conversation with some of my coworkers when we were talking about like, where Cilium as a CNI fits in the stack as it relates to when your application makes a connect call or, what happens. And the difference in these two diagrams really highlights the difference between what happens when you're leveraging Cilium or eBPF to do that networking logic and when you're leveraging, regular routing or IP tables and that sort of thing to do that logic. It's pretty interesting stuff. And like, I think to break into this idea, I'll say that like frequently when you're going to do network measurements, it always comes back to a thing called packets per second. And packets per second is an interesting metric because packets per second are really kind of stuck in the idea that you can only measure network performance as it relates to things that are on the network, right? If the packet's not on the wire, then we can't really measure its performance. It's sort of the assumption that's made when you are locked into a state where you only look at packets per second. And this is actually a great conversation that I had with John Fastabend, who's one of the developers here at Isovalent and does a lot of the work on some of the data path stuff. And what's interesting about that is that it comes down to like, what if you could, for example, drop traffic like you're seeing in the Cloudflare blog? What if you could drop traffic at the socket layer before the TCP stack even is introduced, right? If in this distributed denial of service attack, or maybe there's just bad traffic on your network, and you want to either be able to stop traffic at the socket layer on ingress or on egress, but you want to be able to stop that like as close as you can to the source. So in this diagram, we're describing that like an application pod makes a connect call. And when that application pod makes that connect call, we're able to see it happening at a socket level in the kernel, in the Linux kernel, and then make specific decisions about what to do next. Right, so we could accelerate that traffic. We could pass it transparently through a listener in Envoy. We could do all kinds of interesting things with that traffic before we even get to the TCP/IP stack. Right, the traffic isn't in the TCP/IP flow. There's no IP addresses. There's no packet. None of that stuff is happening yet. This is just at the socket layer, at the application layer. Whereas like more traditional networking models, they actually take that traffic from the app, it goes through the socket layer pretty quickly, and it lands on it is associated with an IP address, and it hits the wire. And so we can measure things like packets per second because this stuff is sitting on the wire. But in these cases where we're operating at the application layer, what's interesting is that this is actually more like how many segments per second, right? This is more about the application layer piece of it rather than necessarily what's happening at the packet layer. And I feel like that was kind of a real eye-opening moment for me in this article. And so definitely take a look at that and see if that resonates with you. I feel like that's actually a pretty awesome thing. Let's see here. What is next on our news side of things? Hey, Alex Barnes. Good to see you. And we got Khalid. We have Russell White saying hello. Good to see you all. It's awesome to see everybody. We also have now version 1.11 of Cilium is out. And so I gave you a couple of links in the notes that you can go check out. The release notes kind of get into, I mean, This was a huge release for us, right? Like, oh, I scrolled down. That's why. Oh, somebody released a patch release for 1.10.6. 1 second. Here we go. So here's the 1.11 release. And I kind of wanted to highlight, I was saying it's a huge release. And right up here at the top, it says a total of 1,395 new commits have been contributed to this release by a growing community of over 350 developers, which is super, super exciting. And some of the stuff that gets into it are, as we get into it, is that we get into kind of like a lot of the functionality that we've grown here. So enabling load balancing on topology-aware load balancing, so honoring topology-aware hints and that sort of functionality inside of Cilium as it relates to service proxy. Open telemetry support. The open telemetry support is actually, in my opinion, like one of the cooler new features that we're bringing to 1.11, and there are a lot of features. So I can't say it's the coolest because, man, there's a ton. But this particular new feature really blows my mind because, like, if you've played with Cilium and you see like the Hubble observability, right? We are able to express network event data in a way that like you could actually correlate with your pods, right? So we understand this pod try to communicate with that pod, or this pod try to communicate with this outside IP address, and we are exposing TCP states, we're exposing timestamp data. There's a bunch of really relevant metadata information that we expose at that observability layer when it relates to Hubble. Imagine that you could take that network event data and build that into sort of the correlation mechanism that you're using for OpenTelemetry. So OpenTelemetry gives you the idea, or gives you the construct for tracing, right? So you might, instrument your application in such a way that you can actually see a transaction moving through a microservice and understand that for that path, the traffic came to this pod. This traffic was had a trace ID, and we can actually follow that trace ID through the set of transactions from the original call from the outside all the way through the system until the response, and kind of understand for a given trace where our system is spending time, like which service did it spend the most time with, within that service, how much time was being spent for particular database queries or what have you. And that's sort of the promise of like the open telemetry and the open tracing sort of model. We can help instrument that tracing model with network event data now, right? So in 1.11, we can actually couple that tracing information that you're getting with the network event data that we are able to expose with Hubble. So now not only would you be able to see like everything that you're already instrumenting necessarily with the tracing, with the trace IDs and stuff that you've implemented on your application layer, but you would also be able to build correlation with what's actually happening on the network. And that whole visibility piece of it just really improves the overall visibility or observability that you would be able to get in a model like this. So that kind of blows my mind, like really, really great stuff. Lots of other good stuff like accelerated XDP fast path load balancing. We actually made some changes to enable the compatibility of STO and kube-proxy replacement. So if you're running in a kube-proxy replacement mode, STO now works a little bit better. One of the things I spent a bit of time working on in this particular release was support for the Mirantis Kubernetes engine. And so lots of troubleshooting there and lots of really good deep dive troubleshooting. And the MKE integration works both with kube-proxy replacement and also with regular kube-proxy. And that was one of the changes that I worked with Mirantis to implement. Before they would run kube-proxy regardless, and now they support the functionality of disabling it. And in disabling it, they do it exactly right. When you mark it as a disabled, if it was already enabled, they go through and clean up so that there are no existing IP tables remaining, etc., that sort of thing. So lots of good stuff. Hello, Yannick from Boulder. Good to see you. Hello, Luis from Portugal. I love Portugal. Such a beautiful place. So yeah, lots of huge changes. And then we also have a blog post. If you want to dig into the blog, that's where this is coming in. So again, like huge release, lots of really great stuff. Definitely check it out. Come try it out. remember that if you go to Cilium.io or isobilin.io, either way, you can see here at the bottom, we have our weekly community install fest. We have documentation tutorials, and then we also have our weekly interactive Cilium introduction, where we'll be talking a lot about what's happening with 111 and all of that good stuff. So if you're interested, go ahead and book a seat and come check it out. On to the meat and potatoes of our session today. Today, I'm going to be kind of showing you a little bit of what I've had to do to test some OpenShift stuff, which I think is actually pretty interesting stuff. And you might find it interesting, or you might find it kind of, you know, maybe not so interesting, but I think it's going to be kind of fun to talk through. So what I've built effectively is kind of a large node. I have a large a node running inside of Google Cloud, and that node has a good amount of memory, a good amount of CPU, and it is got nested virtualization enabled. And so one of the ways that I had to stand this up, I'm actually going to go ahead and add this piece of it because I meant to add this before. We'll talk about why nested virtualization is important. Nested virt. Let me grab that command real quick. Okay, so this is an example of a nested virtualization instance in GCP. And if you were to run this command, basically it would spin up an N1 standard 64 with a terabyte disk in Google Cloud for you, leveraging, and it would use Ubuntu 2004 as the base OS for that VM. And this is going to be where we spend a lot of our time in this particular session, because this is actually the VM that I used as a basis for this configuration. And let's jump in to the VM and start looking around and kind of like talk about why and how and all that good stuff. Zero, so let's do 7, enter. All right. So what I've got here is this N164 VM box, and what I've done is I've installed KVM, I've installed libvirt, and I've installed Vagrant, and I've installed the Vagrant plugin for libvirt. So if I do a Vagrant plugin list, you can see the plugins that I've got installed. I have this group one that I've been playing with, but haven't decided really to commit to. But most importantly, it's this piece here. And this Vagrant libvirt plugin enables Vagrant to use libvirt as a backend. I find that for the most part, people end up using VirtualBox as a backend, but it's not the only solution that's out there. And in my particular case, it was very useful to use Vagrant as a backend. So I ended up doing that. And I want to talk through this setup a little bit. So I'm going to go ahead and do a destroy, and then we'll talk through like how to bring it up and make it work and kind of that whole piece of it. So right now I already had the environment up and working, and I kind of wanted to tear it down and take you through the whole scenario about what's actually happening here. And we're going to do a from scratch OpenShift install here, and we're going to talk about how this is iterable and all that stuff. So before we can actually do an OpenShift install, there's some prerequisites. There are a couple of different ways to do OpenShift installs these days. There's a mechanism for actually using OpenShift where we do a netboot install, wherein effectively we use the OpenShift install command to generate manifests, and then we use a PXE environment to bring up those machines that are going to be part of our OpenShift cluster, and then and that install method is called like UPI or IPI, wherein you're actually going to bring the where you're going to be netbooting machines into your environment, and then once you have those netboot, and then as part of the OpenShift install mechanism, you're pre-configuring them leveraging Ignition and Kubernetes manifests. But to get there, there are a couple of requirements before you can actually even get started here. So one of the requirements is that you need a web server, and I've gone ahead and just did an install of Nginx, and so I have like kind of the standard www HTML setup, and so inside of here I've downloaded the RHCOS images, and I've also and this is actually where I'm also going to host the ignition files, because on our install, which we're going to watch, the ignition files, which are basically the way that we are going to be configuring Red Hat Core OS. Like Red Hat Core OS is configured by basically providing an ignition file. That would be how you set your SSH keys. That's how you install different system units and all of that other stuff. My picture hide the commands. That's a good point. I mean, kind of hides my paste, but what if I do that? Well, but no. How about that? Is that better? It's probably a little bit better. So, so inside of the RHCOS, I've got my installer rootfs for a couple of different versions. I've got the 491 and the 481. And then there's just nothing inside of Ignition that matters at the moment, so we're going to ignore that. But that's my web server that I've got set up. The other thing I have set up is TFTP. And so I'm using TFTP to do the netboot piece of it. And then we're going to talk about how I've wired that up. But inside of here, I have an entry for every MAC address for machine that I'm going to create. And if I look at that entry for one of them, for example, and we can see kind of like what that PXE boot configuration might look like. In this case, when the node gets, does its PXE boot configuration, it's going to basically come up in a PXE environment. It's going to try and load its configuration using DHCP, and then based on its MAC address alone, I'm going to provide this information, right? And so if the MAC address of the VM that's net booting is 52.54.00.00.0101, then I'm going to provide it this kernel, and I'm going to append this initRD with instructions. And this is where we tie in that ignition file with what's actually the installation of a Red Hat OS or RHCOS node. And so this is actually, how we're going to get the root file system. So that's the HTTP URL that is going to hit our web server listening on port 8080. And that's actually how we're going to go get the root file system. And then once we have that root file system, this is what we're going to pass in to configure that node. And we're going to be able to watch that here live in just a second. That's actually one of the benefits of using KVM for this, is that I get a console and we can actually see that. But this is an example of the Bootstrap node. And this is how we're actually mapping that ignition file back to that particular node. Now, a couple of different parts to this. We've talked about the fact that I'm keying on MAC address. And those of you who have been exploring Vagrant for a while understand that maybe it's easy to set the MAC address of the node, but let's kind of talk through the Vagrant file. And then the other piece of it that I also want to show is the netboot file. So first, let's take a look at the Vagrant file. And I put the Vagrant file in the notes, but I'm actually just going to load that Vagrant file up here, and we're going to look at that together also live. So in my Vagrant file, I've got a few different settings that I've kind of pulled up into a config piece right up here at the top. And what this Vagrant file does is it basically gives me the ability to set a domain that will be used for each of the hosts. And I'm using a subdomain, which is called OCP1, and k8s.work is my top level domain. And then I've also created a network called OCP1, and we're going to look at that here in just a second. But this Vagrant file assumes that network exists. So that network must exist before you try and do a Vagrant up. And we're going to talk about that here in just a minute, like I said. Inside of here, I also described the network CIDR that I'm going to use for that network. And this is the CIDR from which the node IP address is going to be associated. And then I'm doing some clever instrumenting of the MAC address, right? So when I'm defining a virtual machine inside of this Vagrant file, I'm going to associate the first six sections of the MAC address are going to be consistent across all of the machines. And then depending on the machine type, I'm going to give the fifth part of the MAC address. And then depending on the machine number, I'm going to give the sixth part. And we're going to look at how that wires up here in just a second. But in this way, I can actually, just by MAC address alone, understand from the fifth part of the MAC address, whether it is a Bootstrap node, whether it is a control plane node, or whether it is a worker node. And that helps me instrument what I'm configuring on the PXE side. So here is the initial bring up of the Bootstrap nodes. And I've got 3 sections here, one for each, right? The worker nodes, the control plane nodes, and the Bootstrap node. And in Bootstrap, I'm only configuring one Bootstrap node, but I've enabled you to actually create as many as you want. And then this is actually where I'm deriving the MAC address. And so this is what I was talking about before. The MAC address that I'm giving to each Bootstrap node is dependent on the number of Bootstrap nodes that we have, right? So for each of the Bootstrap nodes that I've defined, based on the number of Bootstrap node environment variable, I'm actually going to create a unique MAC address that includes the seed, the Bootstrap MAC for the the fifth value, and then the number, like which of the Bootstrap nodes it is. So leading 0, and then which one it is. I'm also enabling the ability to configure how many cores, how much memory, and how much disk are associated with this box. But then we start getting into some of the more interesting configuration options for Vagrant, which is that you can actually use Vagrant to netboot machines, which is actually pretty cool. I didn't actually know about this when I first started digging into it, and it really kind of blows my mind because it really enables like the use case of the user provisioned infrastructure model for OpenShift. And so since I have already defined that OCP1 network, and we're going to go look at it here before we get too far, but I can actually configure this VM not from a base image, but just from an empty disk. And so let's talk through these settings. So inside of here, I'm going to associate this VM with a private network. I'm telling it to use DHCP. The private network name is actually defined as part of the config. So in this case, it's OCP1. And then this is important. This flag basically tells it that when I tear this VM down, or if I tear all of the VMs down, I don't want it to delete the network. I want it to leave that network defined. So let's not delete that network at deletion time. So when I tear down a VM, I want the network to remain. I don't want the network to be destroyed. And that's what this flag does. Auto start false means leave the network alone. The network's already been defined. You don't have to do anything with it. And then I'm also associating the MAC address of the VM with that VM MAC that we've defined right above here. And then inside of the libvirt set of configurations, this is actually where I'm where I'm configuring this node because it's part of libvirt, right? I'm actually, telling it what driver to use. This is a KVM node. This is how much memory I want to give it, how much CPU, how much disk. And then I'm telling it to use for the network I want it to boot from is the network name. So that's OCP1. And then right here, kind of some tricky stuff. If you've dealt with netbooting before, one of the challenges of netbooting is that you have to kind of break a loop, right? So with netbooting, you might want to make it so that you PXE boot all the time. So every time a machine reboots, you PXE boot up. And when you PXE boot in, your PXE configuration needs to be able to hand all of the install bits to your machine so that your machine can do its install. But what happens if you reboot, right? If you reboot, you're going to go back through that same PXE flow, and your PXE environment has to understand how to move you to the next step. Like maybe if there's something on the hard drive, I want to boot from the hard drive. I don't necessarily want to go back through the installation flow, right? There are certain cases where I don't want to reinstall a machine every time it reboots. I can think of lots of examples like that. Instead, what I want to do is on the first boot, I want to do the install. And on subsequent reboots, I want to load from the hard drive. So this trick is really about how do we solve that problem. And the way that trick works is I'm telling it I want to boot from the hard drive first. And then if that doesn't work, I want to boot from the network. And this is clever. So this is a VM that's being instantiated from scratch. It means that the storage that I'm associating, the disk that I'm associating with this VM, is empty. And so the BIOS inside of KVM is smart enough that if the hard drive isn't bootable, then it'll go to the next boot device, which is the network. And then the network kicks up, it PXE boots the VM, we install an operating system on that hard drive that was previously empty. And then on the next boot, on the subsequent boot, we boot from the hard drive. We don't have to go back through that flow. And that's that loop that I'm talking about. Like, how do we break that loop so that when we do the install, it actually makes it all the way through? I also have a section here called Domain Management Attach. And with Vagrant, there's a built-in mechanism that even if you don't define one, the VM will be associated with two different network interfaces if you create a private network. You'll get an interface on that private network, and you'll get an interface on the management network. In my case, I only want one interface, and I want that one interface to be part of the private network. And so when I say domain management attach equals false, it means don't attach this VM to the management network. So that's a pretty good overview of what's happening in our Vagrant file. And you can see that I'm doing that for each of the different machine types. And I broke it up by machine type just to keep it simple to read. But there's a bootstrap one, a control plane one, and a worker one, and they're all exactly the same. I could just iterate through the different types, but I thought it might be easier to kind of see what's actually happening by machine type. One more piece to know about is that I have predefined the network that Vagrant file is going to use. Let's take a look at that. This is the predefined network that I'm using for this. Now, this is actually going to solve a couple of different problems for me. One, this is actually going to be the DNS mask service that the nodes use, right? So anything inside of the cluster is going to be able to leverage this DNS, this DNS mask instance to be able to resolve DNS. And that's important because OpenStack, why do I keep saying OpenStack? My brain, man. OpenShift expects that there are certain host names that have been defined that resolve back to things that are reachable from the cluster. And we're going to talk through like how that's working for us here, right? So this piece here, because I'm actually giving a MAC address, I wanted to also give like a relatively static IP address for each node, so that when the node reboots, it's always going to get its reserved IP address based on its MAC address every single time. And so this problem is solved by basically this DHCP chunk right in here. And that DHCP chunk says that when you boot up, when you give me this MAC address, I'm going to give you this host name, and I'm also going to give you this IP address. And because I've enabled DNS inside of this DNS mask instance, I'm also going to give you a reverse lookup on this, right? So if you ask me what your host name is based on the IP address, then I'm going to tell you the full qualified host name, and we're going to see the magic of that here in just a second, as part of the DHCP mechanism, and also part of the reverse DNS lookup mechanism. I've also configured the PXE Linux piece. So because I configured TFTP, this is actually the PXE Linux binary that we're going to load, and this is our PXE Linux server, and that's 192.168.200.1. And 200.1 is the host IP address of this network. So the bridge interface associated with this virtual network is going to have that 200.1 IP address. And that's the bridge name. It's going to be called the same thing just for consistent naming, BROCP1. That'll be the name of the bridge. I also have extended the DNS mask piece, leveraging the Verse network piece, to include a new schema, which is really pretty neat. Right up here, I've included network DNS mask 1.0, and that enables me to do other cool stuff like enable a CNAME that sends all traffic that goes to this wildcard match, star.apps.ocp1.k8.work, will be forwarded to API ocp1k8.work. That's a CNAME wildcard. So if I were to do host foo.apps.ocp1 ocp1.k8s.work. It's going to resolve to API ocp1.k8s.work. Pretty darn cool. Hello, good to see you. Dan Pop's checking in. Good to see you, Dan. Right on. So that is my DNS configuration for that network, and that's actually how it's wired up. Now, the next question you might ask is, all right, that's all cool, but how did you get it to just work from your host without having to provide that DNS server as your target? That's a great question. So glad you asked. And this is the way that I'm doing that. So I've configured my local system to use Core DNS as its resolver. And I've bound Core DNS on 127.0.0.1. And if I look at my etcresolve.conf on the host, I can see that I'm using that resolver as my resolver. And Core DNS has this great functionality that's called stub DNS or stub resolving. And so the way that that is configured in this core file is that whenever I make a request that ends in ocp1.k8s.work, I want to send that request to 192.168.200.1. And whenever I make a request that ends in ocp2.k8s.work, in case I have two clusters stood up, I want to send that maybe to a different resolver. But right here is how I'm actually sending that DNS request to the correct resolver. And then anything else, I'm actually just using the regular resolve.conf that's actually pulled out of it, right? So the existing one that I got from DHCP. I think that's almost everything. There is one more piece to this, which is the load balancer piece, which is another quick piece we're going to talk through. And I've actually put it in the notes. So if you want to check it out, it's in there. So we've got our DNS, we've got DHCP, we've got NetBoot. Like, this is all pretty complex stuff. We've got our Vagrant file that's going to generate our machines. We've got all of those things. The question is, like, how do I handle load balancing? So I'm going to create one global load balancer on the host and bind it locally. And then I'm going to actually make a pretty interesting configuration of HA proxy to enable multiple Kubernetes clusters, right? And so this one, what this does, this took me a good hour and a half to figure out the right incantation to do this. So this HA proxy configuration is able to terminate HTTP and HTTPS traffic without any certs. It's not terminating the TLS. It's just forwarding it in TCP mode. And that's where you see right here where it says mode TCP, but I'm binding to an HTTPS port, right? So because it's mode TCP, I need to actually tell HA proxy to wait and inspect the SNI header. And when the SNI header comes in, then I can actually use this mechanism to forward traffic back to the correct backend based on the SNI. So this match right here looks at rec SSL SNI and matches on anything that ends in .ocp1.k8s.work and then forwards it to this backend based on that match. And this actually enables me to have multiple clusters stood up on this node if I wanted to test things like cluster mesh as part of Cilium or anything like that. So definitely feel free to crib this. It took me a while to figure it out. And I have all this templated in Ansible, which I might make available as a project later. But for now, this is a pretty good place to start. We talked about TFTP. We talked about DHCP. We talked about HTTP. We talked about HA proxy. We talked about Vagrant. Let's get something started here. Let's go ahead and get something started here. Okay. So you've noticed probably that when I move into this directory, it says something about loading, right? And this is because I'm using DRENV as a project. And these are environment variables that I'm setting when I move into this directory. So if you are curious about DRENV, definitely go check it out. I can't recommend it enough. It is a huge lifesaver. And basically, as soon as I move into this directory, everything that's in my path, I append everything that's in this directory as part of my path. And so if I were to do which kubekettle, for example, that's going to be inside the directory with me. And that way I can just use kubekettle normally. And then I've also exported my kubeconfig to point toward OCP auth kubeconfig, which is where OpenShift puts this stuff. So let's go ahead and create a new cluster. Now, following the way that OpenShift does this, I'm going to make a new directory called OCP. So move into that directory. And then I'm going to copy my install config into it. This install config, before I copy it in there, I'm actually going to do OpenShift install, create, install config. And then if you're going to use OpenShift install to do an install config for stuff, this is actually how you might be able to do it. And, I'm actually not going to go through this process myself because I already have an install config. But suffice to say, this is actually a mechanism for how to do it. I've generated one from the docs in the on the OpenShift side, and I'm going to go ahead and copy that in here. Edit it. And what I'm doing in here is I have a pull secret that I have generated and then I can replace. And this pull secret basically is the thing that you get from the OpenShift install docs, and they give you a place to go grab that pull secret. And then you can make that pull secret available to the install doc, and that pull secret is going to be how you authenticate to the Quay instance or the backend to actually pull down all of the bits to install OpenShift. And then I also have an SSH key, and this is the public key for that I'm going to be able to inject into all of my nodes so that I can SSH into them. And in my case, this SSH key is just the Vagrant ID RSA key that I'm using for this. It's not a private one. But other interesting things about the install config, here's my base domain. That's that k8stat-work base domain. And then down here under metadata, the name OCP1, that's actually where I'm defining the subdomain for this cluster. And then the networking piece, like what CIDRs I want to use, how much of a CIDR I want to give each node. And then right here, super important part, what network type I want to give, right? So by default, I believe it's OpenShift SDN, but I wanted to install my own set of manifests that will install Cilium, and then the server-side network that's going to be used. And then right down here where it says platform, if you go through that installer process, it's actually going to configure all of this for you. But if you don't, then you can actually, this would actually have a bunch of parameters for like the different platform that you're actually applying it to. And then your token would be copied in. This is all covered in the OpenShift install docs. But this is basically how that would work. All right. Now we have our OpenShift, or we have our install doc. And the next piece we're going to do is we're going to generate our manifests. For that, we're going to use OpenShift install. One of the things I've learned about OpenShift install is that the OpenShift install piece is how you determine what version of OpenShift you're going to install. So in my case, I'm actually going to install a 4.8 cluster. And so right here, the OpenShift install version is a 4.8 OpenShift installer. And that means that's actually how I'm determining which version I'm going to install. I'm going to do OpenShift install, generate or create manifests. And that actually consumes the install config. So if I do ls, it's no longer in there, right? It's gone. And then we can kind of look around at what's inside of this. So this is actually the set of manifests that OpenShift is going to use to do the install for this stuff. So I move into the OpenShift directory. These are some of the information. This is some of the information that's going to be used to do the install. And if I look at the manifests, this is the definition of both the CRD for cluster network and also the configuration of it. And so because I had set network type to Cilium, if I look at that, go to config.yaml, this is actually where that is being propagated, right? And if you had set up a bunch of different cloud integration providers or anything else like that, you would also see that inside of here. Other interesting stuff. This is the machine config TLS secret. The infrastructure that we're going to be using, the URL was actually generated, right? So we have API int and API, and these are pointing at OCP k8s.work. And this is actually all that stuff that we put into DNS earlier. And this is actually how we have to define all of this for the OpenShift cluster to install itself. But now that we have our manifests, we want to copy our Cilium manifests in. So I'm going to go ahead and do that. And these manifests are made available. Oop, I meant to move those into manifests. And these manifests are made available from Cilium. And so if you're going to install Cilium, this is actually one way you do it. You could install the OpenShift version or the open source, you could install the enterprise edition or the open source version. It really doesn't matter, but you need to go get these manifests. And you can find them in here. GitHub.com, Cilium, OLM. This represents our manifests. And so for a given version, you can see them here. And so these are the manifests that I've actually copied in. If you wanted to do an install of the open source Cilium, this is where you'd come to grab the manifest necessary. All right, so I've got my manifests injected here. Any other configuration that I wanted to do to the cluster beforehand, this is the time to do it. So if I wanted to like maybe disable kubeproxy at bootstrap time, this is actually where I'd be able to make that change. All of that stuff would happen here. What do you mean, what about proxy? What is the proxy part that you're asking about? I'm happy to answer the question. Once I have that all turned on, I want to go ahead and load this up. Or I want to go ahead and generate the ignition files that OpenShift will do to do the install. So again, I use this OpenShift command. I do create ignition files. And this bundles all of these manifests up, and it makes them available as part of a Bootstrap configuration for the Bootstrap node, and also for anything that is necessary for the machines. All right. So now you can see our directory has changed again. Now we have a new directory called auth, and we have these ignition files. And if I do a tree here, find dot, we can see that inside of the auth directory, we have this kubeconfig, and we have kubeadm password, or kubeadmin password, which is the password that is going to be used to lock it in. Which proxy is used? Still not sure what you mean. So right now, OpenShift by default will install kubeproxy. That could be the proxy you're talking about. I'm actually not sure which question you're asking me. So one of the other things I'm doing here is I need to make so that all of the ignition files are world readable. So IGN. We can see now they are all world readable, and this is important because I'm about to copy them into the web server. So let's go ahead and copy these ignition files right into our web server. Var www.html ignition OCP1 for this cluster, and then paste them in there. And so now my web server has the file, and I can actually see it. Right? I can do curl localhost :8080 ignition OCP1, and then we'll look at like worker.ign. Right, so that's what a ignition configuration looks like. Might be kind of more interesting to look at the Bootstrap one. I think this is actually pretty cool. This is actually from the CoreOS days right here. Bootstrap. What is it called? It's called Bootstrap IGN. Oh, I missed the P. And then I'm going to pipe it to JQ. Ah. Update my automation to install JQ. So this is a Bootstrap. This is a very big and complex Bootstrap or ignition configuration. And what it's doing, let's go ahead and way up at the top. Actually, let's just pipe this to this. Save myself some time. it's telling it what version of Ignition to use, and then it's setting up some users, right? And so because we've actually passed in the SSH key that would be used, it's populating that SSH key. Interesting. It's populating 2 SSH keys, but I'm only providing 1. That's pretty fascinating. So Core is actually installing 2 different SSH keys. The one that I provided, and some other one that I'm not really clear on why that's happening. Might be kind of an interesting to look into. And then on the storage side, it's going to go ahead and configure these files, right? So it's going to set the registries file. It's going to set, this is the value that it's going to, the contents of that file. It's going to set the MOTD and the contents of the MOTD. It's setting the CA certificate for the CA trust. A bunch of other information here. But if you're curious about Ignition and how it works, this is definitely a place to look. And so that token file that I'm using, that I'm providing, that's actually being made as part of the docker config.json. So this token will now apply for any Docker pulls or for any image pulls, regardless of the registry or regardless of the container runtime used. And in OpenShift, they use Podman to do this. And then here's Bootkube. This is actually how we're going to do the installation of the cluster. And we'll kind of look through that here in a second. All right, so now we got all that working. Let's go ahead and bootstrap our machines, right? So here's our Vagrant file again, coming into handy. Vagrant up. Vagrant up is actually going to begin that bootstrapping process. It's going to create those machines, and all of those machines are going to net boot and load up their respective Ignition files and configuration. Now, a part of the magic here is that inside of the serve TFTP, I want to show you this real quick. Pixie Linux CFG. A part of this is that right in here on this command line, I'm also setting the console line. I'm telling it to use as a console the TTY-S0 console. And that means that if I connect to that, I'll be able to see what's happening as it loads up. And because this is in libvirt, I can actually connect to that, right? I can do console domain OCP1 bootstrap 01. I can see what's actually happening as the thing boots up and follow along what's actually happening at boot time. And so what happens is it went ahead and it bootstrapped. I mean, it's gone ahead and loaded itself up, and now it's actually going through the process of becoming a fully installed machine. And so, like, we boot that live kernel configuration right off of the TFTP server. And as part of the initRD of that environment, it's going to try and do an install, right? And so you can see this is the result of what was passed as part of the TFTP configuration. Pretty cool. What it's telling itself to do is go ahead and resolve its IP address via DHCP, and then use this CoreOS installer command to do an install against dev VDA, which is the only disk on the VM, using the Ignition URL to do the install. And so it goes ahead and goes and copies that whole install operating system down onto the disk. It's basically like doing a DD right onto that VDA disk. And then once that copy is done, it's going to use Ignition to do the install. And we'll be able to watch that happen too. It's actually a bunch of really interesting machine parts. And what's funny about this is a ton of this is actually from Tectonic. Like a lot of this is like related to how we would do it in Tectonic. And it's really kind of wild to see this happening on Red Hat Container OS, because like it really does represent that, like a lot of the work that we did at CoreOS, Red Hat was like, yeah, let's do that. Let's just make that happen as part of OpenShift 4. And so the whole install process is like almost line by line how we would do it with Tectonic. We would use Matchbox instead of a lot of the mechanisms here that you see, but like it's effectively the same premise. So we got our disk laid down, and now we're doing a reboot again. And this is neat because we're basically watching this all happen over the serial console. And now we laid all of those ignition files down in the initRD. So the initRD file system has all of that ignition stuff in there. And now what's happening is ignition, before reaching the live OS version of it, ignition is doing all of the work to lay down all of that configuration. Right? And so here is the first boot. We're checking the disk. The disk looks okay. And then we're going to go ahead and start ignition. And then we're actually reading the ignition file in, reading all of those ignition files in, and then we start laying things down according to what we see in that ignition file. Right? So making sure the partitions are set up correctly. And then we're laying down the base ignition. We're making sure the partitions are all correct. And then we're starting to write down those files that we created. So the first one that we saw was that ignition machine config encapsulated, right? So there's that file being laid down on disk. We're laying all of this stuff with ignition right down on disk. It could be system D units. It could be partitioning file systems. It could be configuring interfaces. All of that stuff is on the table with ignition. And now we can see that the machine understands who it is and it's effectively installed. Ignition happened all of that happened before it reached runtime. So now I can actually do Vagrant SSH bootstrap 01, the first machine. And because I populated that public key with the Vagrant private key, I can just Vagrant SSH in, right? And so when you SSH into a CoreOS or into a Bootstrap node, we can actually see what's happening here. So this is the configuration of the temporary control plane. So even before the regular control plane nodes boot up, this bootstrapping node is being used to hold a bunch of information about the cluster before those control plane nodes boot up. And this is actually watching the process of how this works, right? And so we can see that we've stood up a temporary control plane. This is the API server. And now we're starting to populate that temporary control plane with a bunch of manifests. And if I do kubectl get nodes, we can see that there are no nodes that are registered yet, but we can still see the API servers responding, right? Like there it is, right? Get svc-a. You can see that the services are starting to be defined. Right. Cilium EE-OLM has been defined as a service. We can do get pods-a, and we can see if there were any, they would all be in pending. But there aren't any yet because they haven't been defined yet. Another great command is get cluster API resources. So our API server is responsive. The configuration that we have allows us to authenticate to it even before the cluster exists, right? So now we're starting to see all of those things show up. Here's a bunch of stuff from the OpenShift side, populating all of the CRDs. Things are starting to come along. And it's a little unresponsive at times probably because the nodes are starting to come up. So if I do get nodes, there we go. We're waiting for the API server to get all the way through this part of it. And OpenShift actually provides a really cool an extension of this OpenShift install command, right? So I can do OpenShift install wait for bootstrap complete. And then I pointed at the directory where I have put all of that manifest stuff. And it will actually tell me when that is complete. So in the meantime, I'm going to go ahead and open another terminal. Oh, We'll put that right up here. Oh, got to move into the directory. Hey, our machines have now registered with that temporary control plane, and they're presumably kind of getting all of their stuff and starting to come up. So here we can see the certificates being generated for these, right? The node certificates are approved and they're starting to kind of get applied to the nodes. Our control planes are starting to come up. Hmm. Okay, I think in my testing, I may have messed something up. We can probably fix it. Edit, deploy, dash in, Cilium, EULM. Yeah, I think I was pointing at the wrong image. Nope, still doesn't work. I think I messed something up. One moment here while I fix this up real quick. There we go. All right. Now, keep watching. We should also see this Cilium EEOLM operator. Go ahead and install Cilium for us. And this is just using the Helm operator tooling that is a part of like the Cilium stuff or part of the OpenShift ecosystem. There we go. So now we're starting to see our Cilium agents come up. Pretty exciting. . Other interesting things about OpenShift. You have 24 hours to get a cluster installed. Otherwise, the certificates expire. The CA certificate expires, and then you can't proceed. You're going to have to kind of reiterate. You're going to have to iterate over the thing again. Other things you can do now. So if I can do kubectl get cluster operators. And this tells me like where we're at in this process, right? So we're waiting for things to come up and move through. Ideally, in a complete cluster, we would be able to see it completely move into a bootstrap phase. And so at the moment, we're waiting for all of the pods to actually come up. So if I do kubectl get pods -aw, we can kind of see that starting to happen. So a bunch of containers are in creating state. A bunch of containers are kind of starting to come up. And this is actually, think about it as we've got our bootstrap cluster, our bootstrap API server up and running. And right now what we're doing is we're loading the control plane onto those new control plane nodes that I've registered. So all of the pods can't actually instantiate until you put control plane nodes in them. Now those control plane nodes are there and they've reached a ready state. So if I were to do get nodes, you'll be able to see they're in a ready state. So now each of those nodes is starting to load all of the pods that are a part of the OpenShift operator ecosystem. Now, there's some really interesting transition points in this process. Part of the transition, one of the interesting transition points is we had, if you think about it, that temporary control plane had its own etcd. And so that API server and etcd that was on the temporary control plane located on the Bootstrap node was actually the source of truth for the whole world. And when we joined the other nodes to it, we were sharing that one etcd node. And that means we had a quorum of one, right? There's not a quorum of one, but we had an etcd cluster that was sized with a single instance. So now as we join these new control plane nodes, that it becomes a set of 4 etcd instances, right? 1 etcd instance per control plane node and the one on the Bootstrap node. And that means that quorum will effectively have changed. So at some point, I expect the API server to become unresponsive because, and no, not all nodes have to be a master. I'm only spinning up control plane nodes, but maybe after this, I'll spin up some worker nodes too. You can do that too. But for my testing, most of the time, I could just do that with 3 control plane nodes and understand whether things are going to work. But you can absolutely create worker nodes as well. So when you change from 1 etcd node to 4 etcd nodes, that's a quorum change, and that means that like everything has to kind of go through a whole election process, and that etcd becomes unresponsive for a period of time while that's resolving itself. Kind of interesting stuff. So this bootstrapping phase is really about making sure that the control plane, enough of the control plane stuff, there it went. Yep. We're waiting for enough of the control plane stuff to move to the cluster that we can then tear down our Bootstrap node because it's no longer needed, right? So until we have all of our configuration and all of the running and moving bits in the OpenShift cluster that we're installing, we have to keep that Bootstrap node around. And then once we get everything installed, then we can go ahead once we get the control plane stuff onto those control plane nodes, then we can tear down that Bootstrap node and throw it away. And we're going to do that here in just a second once we reach that state. Yeah, great question. The answer is, the question was this. Do all the nodes have to be master? And the answer is no. In my case, when I did the Vagrant up, I only brought up 3 control plane nodes and 1 Bootstrap node. But the Vagrant file that I have as an example definitely supports the worker nodes as well. Now, when you bring up worker nodes, the challenge is you run into a different problem, wherein if you bring up worker nodes, you have to actually you have to approve their certificates in OpenShift yourself. There's no automation that will approve that certificate for you. And you know what? I can actually, yeah, you know what? Let's just go ahead and add a worker node to this cluster. But we'll do that in a while. once we get through this bootstrapping piece, we could probably work through that. So we're still in the place of like, moving pieces back and forth between the temporary control plane and the persistent control plane. And in some ways, this is sort of analogous to the cluster API mechanism, right? Where you like bring up a temporary control plane and then you like, move things back and forth between the two. And then you can tear down your temporary control plane. Like we're getting there. Things are almost working. If I do cluster operators, I can see that there's a lot more information now. Oh, bootstrap is complete. And did you see the break again? Like the break now happened because I just removed an etcd node, right? So I'm going to do vagrant, destroy, bootstrap 01, because it's no longer needed. Yes. Now I can run a different command. I can do OpenShift install, wait for, install complete, log level, debug. Here, OCP1. Now this is neat because we can actually watch the install complete. So now we have all of the control plane stuff necessary inside the cluster for it to survive. But you can see that not everything is completely done yet, right? So we have authentication in a degraded state. We have the DNS in a degraded state. It's always DNS. We have monitoring in a degraded state. We have, yeah. Now we're watching those cluster operators do their work. And the neat thing about this is that if you wanted to dig into like how the cluster operators work, their naming is very consistent and it's easy to kind of dig in and like see what's actually happening in a particular space. So for example, this authentication piece. Log session OpenShift -authentication -operator. And then we can actually look at what's happening in the logs. Which isn't really telling us too much at the moment. So it's telling us that when it's trying to start up, it's not able to start up because there's stuff that's missing. It hasn't been populated yet by the operator itself. But we're making progress. Looks like authentication is still progressing, but it's no longer in a degraded state. We have insights still. Actually, we have the Kube API server in a degraded state, presumably because we're doing an update here. One of the things that's interesting is that when you do an OpenShift install, one of the first things it does once it gets everything in the control plane is it goes through and brings you to the latest patch release. And so if you haven't installed already to the latest patch release, then it's going to go ahead and do that work for you. Almost there. The other fun thing is that part of that patch release upgrading also takes out the etcd cluster again, right? So not in a degraded state, but then it's like basically updating the etcd operator, and that updates the etcd nodes, and that means that you have to take another hit while the etcd nodes restart. Reach quorum. Waiting for things to come back here. %97 complete. API service really slow right now. Which might be related to this bit of it here, where it said the Cube API server is not in a healthy state. Oh, looks like it just came in. There we go. Graded false across the board, which is great. But we're still progressing on a few. Nearly there with the install. Oh, there we go. The leader changed, right? It's kind of an interesting output from kubectl, because kubectl actually, the API server forwards that error from the API server back to kubectl. So that's how we know that the etcd server leader changed. And we can see that happening right here, right? etcd is progressing, which means that it probably took the update that we were talking about up here, and that's where we saw the change hit again. So it looks like etcd availability is true, no longer hung up. And then we basically bring up the kind of restart the whole update process one more time, and then we iterate. Many of these are already done, so it's basically just going through saying, have you already done this update? The answer is yes. And it gets to a 661, and it's like, that's something I haven't done yet. Pretty awesome stuff. I hope this is useful to folks. I found it pretty interesting, and it's a really kind of it's one of those like, there's a lot of context that is shared here that I've gathered over the years, but I don't know how useful it is to everybody else. So, but if you find it useful, let me know. I hope it's useful. The neat thing about this is this can all be thrown into an automation state, right? Because like this is all just leveraging a Vagrant cluster, so we can throw this stuff into like automation and like testing, so that when we release a new version of the Cilium operator, then we can actually validate that piece works correctly. We can push the tests for the operator up. All of that stuff can be automated. Pretty exciting stuff. So waiting for it to get past 661 here. That should be it. Looks like it's nearly done with the controller manager. Still progressing. Yeah, it shouldn't matter like how you actually go about doing the install. You could use Cilium on any of that stuff, whether it was installed on VMware or AKS or EKS or what have you. I brought up this environment specifically because I noticed that a lot of my, I have a number of folks that are actually leveraging bare metal installs for OpenShift, and I think OpenShift targets the bare metal case pretty well. And so this environment was about how do I reproduce like bare metal installs. But yeah, you could do it on VMware, AWS, CKS, anywhere you can deploy OpenShift, you could deploy Cilium on top of it. So we made it out of 661. Now we're on to 675. I sometimes joke, and I mean this in the kindest way, that OpenShift should kind of rename itself Operator Shift, um, because my goodness, there's a lot of work that happens in a cluster that is part of this whole machine. You know, like it's a lot of steps, it's a lot of pieces, a lot of moving parts, and they do an incredible job of orchestrating it. Um, and I remember even thinking this was true of Tectonic, and we had way fewer operators at the time. But like there's a lot of moving parts to this and how it's managed. It's pretty amazing. Pretty amazing piece of engineering. I mean, just the words I've thrown out there thinking about how we're managing just bringing up this like bootstrap environment. Like that was already a lot of complexity. Now think about the complexity of orchestrating all of these operators and everything. Amazing. Absolutely amazing. 99% complete. We're almost done. I want to see us cross that finish line before I call it. To all the way across except for the API server and the authentication piece. Almost there. Good stuff. I mean, this is actually kind of their internal implementation of Cluster API, the machine set stuff. Hey, almost done. Waiting for this thing to finish up, and then we will call it a day. But I want to see it actually happen. So bear with me while we wait for this, but it shouldn't be too much longer, and then we will be good to go. There we go. Edit machine configuration. Oh, we're so close. We're waiting for the API server to finish its thing. And then we'll be finished. Hey, we did it. All right, we've hit. And so the neat thing about the OpenShift install wait for install command is that it also gives you this information here, right? It tells you that your install is complete, tells you where the kube config is, tells you how to reach the console and the admin password, all that stuff. And here we have our working Kubernetes cluster. So the one thing I wanted to do, let's see, I want to go back up here, worker count. Let's add a worker, and then we'll be done. You're in up worker 01. Oh, 301. CD bar. All right, then we should see that boot up, and then we can go through it. But one way or the other, we've gotten through the whole thing. Yeah, that 1% is the longest. It's always the longest. I think I'm actually going to call the session because it's about an hour and a half after we started. I feel like we've covered a ton of ground. I hope that some of this was useful to you, and I hope that you find it as interesting as I do, because like infrastructure has always been a thing that kind of fascinates me. So I spent a lot of time working in that space. If you have questions or you want to chat about it more, you can hit me up on the Cilium Slack or on Twitter, and I'm here to help. It's what I do. I hope you have the best weekend of your lives, and I will see you all next time. Hey, there it goes. Maybe I'll give it 2 more minutes. Hold on, because I think this is kind of interesting. So let's wait for this. Let's see if we can get all the way through the install here. All right. Thank you all. I'm going to go. I'm not going to wait. I'm going to take off. Have a great weekend. Thank you. Thank you. Thank you. See you next time. Bye.